In this video, we will try to get an idea about what is displacement current. To understand displacement current, let's begin by revising something which we have studied earlier, the Ampere's circuit law. So let us say there is a current I flowing through a wire, and I'm interested in finding out the magnetic field at point P, which is r distance away from this particular wire. So we apply Ampere's circuit laws. For that, we take a circular path of radius r. We're interested in finding out the magnetic field over here. By using the thumb rule, we know that the magnetic field direction will be upwards over here, coming out of the page, going down over here. This would be the direction of the magnetic field. And if I take small lengths along this is dl, and this is p. These are all the magnetic fields. So if I take small dl along the direction of p, then I can apply this over the entire length, and I'll get the equation for P as mu naught upon 2 pi and I upon R. We have already done this, so I'm not going into the total derivation of this as to how did we get this equation. So the magnetic field at point P will be mu naught upon 2 pi I into R. Now it turns out that Ampere's circuit law is not applicable in certain scenarios. In fact, it is not, instead of saying not applicable, it's more correct to say that it is not complete. So let us try to understand a scenario where we cannot apply Ampere's circuit law. So what I'll do is I'll take, let us say, a circular plate. In fact, we'll take two circular plates which are part of a capacitor. So I've taken a capacitor over here with two circular plates over here, and this current is increasing in this direction, and therefore this capacitor is getting charged. So this capacitor is getting charged. And now let us say I am interested in finding out the magnetic field at point Q over here, which is between these plates. So let's try to apply Ampere's circuit law to this particular point Q. So again, I'll do the same thing. I'll take a circular closed loop, and this is the area of that loop that I have taken at this particular point Q, and let's apply this. So I will use integration of B dot dl is equal to mu naught I. Now if I look at the right hand side, we have current over here. Now what is the current which is passing through this area? As we can see, these are two capacitor plates, so there is no current passing through this. The current is 0. So therefore this will turn out to be 0, and therefore magnetic field will turn out to be 0. So if I apply Ampere's circuit law as it is, the magnetic field at point Q turns out to be 0. But when practicals were conducted, experiments were conducted, it was seen that there is a magnetic field over here. So there exists a magnetic field over here. When a magnetic compass was placed over here, it showed deflection. So then how do we resolve this anomaly? According to Ampere's circuit law, B equal to 0, but in practice there is a magnetic field. And that's where James Clerk Maxwell comes in. So he tried to give an explanation for this magnetic field. So he said that let's ask a question that how is a magnetic field produced? Or before that, how is an electric field produced? So let's begin by asking this question as to how is an electric field produced? So we know one way of producing an electric field is to have charges. Charge will produce an electric field. The other is, we know that EMF E is equal to d phi b by dt. So by Faraday's law of electromagnetic induction, a changing magnetic flux produces an EMF, and an EMF would mean there is an electric field produced. So this is another way of producing electric field. That means a changing magnetic flux produces an electric field. Let us do the same thing for magnetic field. So how is a magnetic field produced? One could be by magnets, or you could say by current. So this is one way of producing a magnetic field which gets covered over here. There is a current in this equation which produces a magnetic field. Whereas here there is no current but still a magnetic field is produced. So Maxwell argued that is there any other way by which a magnetic field can be produced? And he proposed that a changing electric flux d phi e by dt can also produce magnetic field. The way over here a changing magnetic flux produces electric field, he said that by symmetry a changing electric flux can also produce a magnetic field. So if you go back over here, we know that charges are getting deposited on this plate. That means an electric field is being produced in this place, and this electric field passing through this area, this particular area which we have marked, that electric field is changing. So we have d phi e by dt over there. There's a changing electric flux passing through this particular area. And he proposed that this changing electric flux produces a kind of a current through between these two plates. So he suggested a change in the formula for Ampere's second law. He said the formula could be written as integration of B dl is equal to mu naught I plus, we should have here, he said, one more term which brings in change in electric field, because change in electric field also produces magnetic field. And he said that that would be equal to epsilon naught d phi e by dt. Now at this juncture we will not get into the derivation of this, but he proposed this term to take into account the magnetic field being produced by changing electric flux. And this equation is known as Ampere-Maxwell equation. Thus, this takes care into account both possibilities, magnetic field due to electric current and magnetic field due to changing electric flux. Now the question is, what would be the unit of this particular term? Obviously in physics we can add only physical quantities having the same unit. So obviously this also has to have the unit of electric current. And if you take the units of epsilon naught d phi by dt, it will turn out to be ampere. And therefore Maxwell called this particular current as the displacement current. Displacement current, will denote it by ID. So this is displacement current, and this we will denote it by IC, which is known as the conduction current. This is the usual regular current that we refer to when we refer to any electrical circuit. So this is known as conduction current, the regular current, whereas this is known as displacement current. Now it doesn't mean that there is an actual current flowing through this. It simply says that this change in electric field or change in electric flux between these two plates creates the effect of a current and thereby produces a magnetic field. Therefore, this is equivalent to saying that there is an electric current flowing through this particular plates.